Yeah, so because it's like a lecture kind of class, I switched a little bit. Instead of being only a research talk, I made some basic stuff that I think could be related to my work in high-order interactions, and then I present some things related to my work in TDA, high-order interactions and data. Then I split this in like 3 parts, and each part I hope that takes about 20 minutes, but then I raise some questions for the students to be in breakout rooms and then come back with answers. So I gave 6 references, but actually I only suggested to read one that gives an overview on phase transitions in physics and topology. And because topology relates to high-order interactions via like topological data analysis and stuff, so the link is summarized in one reference. Okay, so then what I want to tell in the first part is very basic, but then builds up to the other things that you've seen in high order. So then I come from the Erdős-Rényi graphs, like from the really random graphs, and then the idea of phase transitions, and then whether this idea exists or not for high order interactions, and what are the difference. And then we see whether that extends. And then, okay, as I just say, like, what are those type of graphs? So what's this work in Erdős-Rényi relates to high order interactions? Then I build up homology and Betti numbers. How do they ways to come as a generalization of Erdős-Rényi graphs? And then we know that Erdős-Rényi graphs has these phase transitions on the giant component. So where this transition extends to high order. And then this gives some sort of overview of one thing that we knew very well, let's say in pairwise topology or pairwise graphs, and that we extended to high order interactions. And then if that idea can be extended to other types of approaches. That would be what we're going to discuss in a breakout room. Okay, so then introducing like I think this is possibly the most cited work by Paul Erdős, even though he's, for everyone here has some Erdős number, but it was basically a model where you have like a graph, and then you can choose at random uniformly. If you have a graph with n nodes or n vertices, you have a uniformly choose m edges or m connections, so that then you have a notation G and m. Or if you fix the probability, so if you have for all possible pairs of edges, so n choose true edges, how you can independently find the links between those edges with probability p. So probably most of you already heard about these. Then basically it's not necessarily, oh, sorry, I missed my screen here. So probably this is not new, but then the key phenomenon is that as you increase the density of the graph, so if you increase the probability, when the probability reach the value 1 over n, where n is the size of your graph, you have the so-called giant component transition. And that's the transition I want to start with and then build up to other types of transitions. Any questions? Okay, so then I continue. So then this is a type of example that we can generate. That is from Wikipedia. And I created some sort of a small video on this type of Erdős-Rényi graph. So you can start with an empty graph, and at the moment you increase the probability of connecting random graphs, you start from like an empty type of graph to a dense type of graph. So all the parameters, the emergence of this giant component, when the size of the largest component of the graph is the order of magnitude of the size of the graph itself. And that's the Erdős-Rényi transition. So I put a reference to Erdős paper, so then that if you read it, you can see like the actual derivations, how this goes. But what I wanted to discuss is actually what comes next, because now we are in like a high order. Let me put back to the full screen. Okay, so then, as I said, for critical probability, this cycle emerges nearly certainly, and then there is this is a threshold for graph connectivity. So that's like most surely for very large n, you have a fully connected graph. But a property that this graph has, at least in the pairwise case, is that this happens smoothly. So at the moment you keep adding more links, like if you increase the probability, the giant component of the graph grows slowly. So that's a signature of or in physics, they call it a second order continuous phase transition. So the transitions are smooth. So if you have a small change in your parameter, in this case, probability, you have a small change in your property. In this case, the size of the giant component. What happens that you probably heard in other talks and in high order interactions that this is not the case when the system is high order. And that's why I chose, okay, I will talk about phase transitions. I start first round like more theoretical, because as far as I know, the first example where this phenomena happened, like or what the transition is different for a high order system, is in the generalization of Erdős-Rényi transitions to simplicial complex, to high order structures. Of course, each field had your own generalization. Like in dynamical systems, we have these generalizations. In other fields where you move from pairwise to high order, you also have to check what happens with the phase transition that already exists. So people already knew in pairwise how it happens in high order. But I think in terms of chronology, like this was also one of the founding papers of at least stochastic graph theory. Proportionalization is good to know which paper made this jump. Okay, so then to make this jump, I build up back in the Erdős-Rényi graph. It's basically what you don't want to happen, like the giant component you want to have. The phase transition is before the phase transition, you don't have loops in the graph. Essentially, you have lots of trees. And after the phase transition, you have loops. Like so before phase transition, you have multiple small components. And after the phase transition, you have nearly one single big component. And then the more dense the graph becomes, like a higher probability, then you approach to one single component. The nice parts for high order that the whole all the tools to extend this approach to high order is already known from topic called algebraic topology. And when you apply this to data, to topological data analysis, which would be like algebraic topology applied to data. So then what you need to know is basically to generalize the idea of a cycle. And that's the concept of homology. So in mathematical terms, homology of size n will be the extension of concept of cycles for dimension n. So if homology of dimension 0 would be just connected components, homology of dimension 1 would be loops and cycles, and homology of dimension 2 and so on would be high dimensional holes. So for the moment now, I don't need to come on how to implement that. I can see it later, or I can give us reference on how to implement these. But basically, you see that it's very natural to generalize the idea of Erdős-Rényi, at least if you learn a little bit of algebraic topology, because you would build this generalization via these homologies. So then the Bethe numbers are then the dimension of this homology group, but for like a more pedestrian understanding is that a Bethe number is basically the number of high dimensional loops that you have in your network. Then you can have the same question. Okay, if Erdős and Rényi, they made this question of what's the critical probability of having a giant component in a graph, if I make the same question, so I have a stochastic topology, that's the topic, the main topic of mathematics that study this type of problem. So if I have high order structures, in that case, simplicial complex, like simplexes, that I assign some probability for emergence of each simplex. So I have a simplex in this case to make analogy with Edwards-Henry graph with a constant probability. Is there any critical probability to see those bad numbers of this homology when the system become large? And so is there an analogy between Edwards-Henry and random simplicial complexes? Yes, and that's nice, because basically that's the paper the second reference I say I would like to discuss. So then it's like instead of having a random graph where you have vertices and then you have fixed probability to connect them P, I have now a random simplicial complex. It's still a stochastic process, but I would have simplexes. I will have any simplex and a fixed probability P of them being connected. So in an independent way. So basically for D equals 1, I would have Edwards-Henry graphs. For D greater than 1, I would just have a generalization for simplexes. So there's the extension, and I think that was the second reference. And okay, maybe that one was a bit heavy in the maths, but I just wanted to highlight that this is a fundamental result in high order interactions that is nice for all the PhDs to know, because this happen in so many other fields and so many other applications that I would like to share this, let's say, the original pure mathematics paper that has this result. So in the same way that graphs have thresholds for connectivity of cycles, high dimensional complex, simplex, they also have a threshold for emergence of one cycle, for 2 cycles, 3 cycles. So that's kind of an analogous result. But there is a surprise. Basically, instead of having the emergence of giant components in a smooth way, so let's say for normal graph, every time you put a new link, then the size of the component becomes bigger but smoothly. This giant component of a simplicial complex already start giant. And that's what Lineal and Pellet showed in 2016, like more rigorous paper, and they started to develop in 2006. So they came with a concept of shadow, because it's easier to study some sort of complement of the graph. So basically, the set of edges that are not in the graph, but when I put in the graph, I create a cycle. Let's say if I'm very close to a phase transition in a normal graph, an edge will be in the shadow if every time I put this new edge in the graph, I create a loop in the graph. So then it's any new addition creates a loop. So then it's like when I put this, I started being in the phase transition in a sense. So in pairwise, it's easy to draw. Like I have lots of trees and I reach a critical size of any moment I put a new edge, I connect so many trees that I can create a loop. And that is where I cross to the phase transition point in a graph. So if I think that in high dimensions, I would say, okay, let's think about triplets. So then if I have lots of triplets and I put a new triplet, and the moment I put this triplet, I create a cycle, one cycle. So then the addition of this high order simplex would create a new structure, a new high order structure. What is surprising from this result is that the transition is not smooth. The transition is sharp. So in the left case, you see like the Edwards-Henry case. So basically, if I increase the probability threshold, basically I don't have any giant component, and at some point I have a giant component that is kind of growing smoothly with the size of your parameter, like probability threshold. Whereas if I'm in the high order case, so if I'm in a simplicial complex case, basically there will be a moment that your simplicial complex is so dense that nearly any simplex I add to the simplicial complex, I create a lot of homologies, or I create a lot of loops. And that's like geometrically it's illustrated by this graph in the paper by Lineal. Just basically that then the size of the giant component in a high order graph or in a simplicial complex is already gigantic. So that type of plot, I think you already saw in many other papers. I don't remember seeing this before this Lineal Pellet paper. Like this paper was published in Annals of Mathematics 2016, but I think it was in Archives 2015 or even earlier. And I think even some colleagues on BeyondTheEdge has results like that. I think Giovanni has a paper in dynamics like that, or Chris, that high order interactions are one possible mechanism to create discontinuous transitions. But because let's say most of you are doing PhD in mathematics, I think it would be nice just to show this result. And then even though this is like in relation to percolation theory, because it's like adding links in a way that assorting the links with certain weights, in this case the probability, and then at some point you have a critical threshold where you have a percolation. This fact that the transitions in high order are often discontinuous is nearly ubiquitous, like nearly every high order system has this behavior. But I would want to highlight this example also because it relates to my work that presents in next round, and that's why I want now to make the breakout rooms and so that you think, because probably you got already many talks, you have all your 10 supervisors, 10 co-supervisors. So, and one way of doing this network is basically, okay, so easy way, if we have to do more than that, is that basically you see some pairwise mechanism, pairwise models that you already know, and then you try to make it a high order version of it. Of course, you should not choose it at random, should be meaningful, something that you like to see high order, what high order gives more than pairwise. So then this was one example, and each PhD will do one other one, but of course choosing a specific field with some reasoning. So what are the analogs you see from that? I already mentioned that maybe there is dynamical analogs, like this kind of that I just mentioned. And what are other possible giant structures that you already saw beyond these homological cycles? They also exist from other colleagues in the network, but that you may know. You know any real-world context where you would see this helpful. So I would just leave you to come for 5 minutes in Paris to chat, and then each one gives your answer. Then I show my work. It was more, I start making this more a class rather than a research talk. If anyone has questions, I can answer, or otherwise you just go to the breakout rooms and come with your answers. So this is a work that probably some of you already know, because it was one of my main work that I start this field. Is a paper on where we investigate topological phase transitions in brain networks. But before arriving in the brain, I will go through the analogy with physics and what happens in the networks, like in this Erdős-Rényi type of generalizations. What I did was when I was in Brazil, but I still do work in this, so what starts in Brazil. So that's where I come from. Like some of you came there, I heard, like where this is Carnival in Recife. The first plot of this is the temperature plots, like a minimum 25, maximum 32. So it's a very good plot and nice beaches. But the question is like, okay, we always want to investigate, let's say most of us in this network wants to apply high order methods to complex systems, to network science. And I will not come with a precise definition of what a complex system is, but I will make one that is nice for topology. So then systems whose dynamics or interaction are difficult to know, intrinsically difficult. Like when you measure a system, you cannot measure the model that is underlying the system. You can say, oh, I have a complex system. And then you can come with your favorite methods in mathematics that try to model or to understand such models. And then what I will show you is that then algebraic topology or topological data analysis is one of those candidates. One nice part is that in the past there was a lot of discussions, especially now with AI, is that then you maybe don't need these mechanisms. Some people say, oh, you need, but some people say, oh, you don't need, or maybe you need a mechanism that's independent of knowing the model. That's more like many questions in either dynamic systems or in topology or in statistical physics. So in a complex system, I don't know anything about the model. How can I still get any information about that system? And then I will just come with this tool that basically topology. So the properties of space that are preserved under continuous deformations. So there's this topological kind of joke. So you can always deform continuously a donut into a cup. So for a topologist, there's no difference between a coffee cup and a donut. And then I want to do this second part, how topology can contribute to understanding complex systems. I will show this analogy between phase transitions and topology. Then this again refer to the Edge-Henry transition. Then they do a bit intro on TDA, and then applications into the brain. So in a way, what I used first that's more mathematical in topology was not related to discrete data, but to continuous data sets. Is the so-called Morse theory. So it's when you make a slice in a hyperspace, you basically can understand those hyperspace by understand the potentials of those hyperspace. So if you have a torus that you make some slice, or put torus in a coffee, so the most important slice are the one where you see critical change. So then the slice between the minima and the first handle of the torus are not trivial, like there's no topological change. Only when you reach a level where you really find this kind of critical point in a torus that you have a critical change. And again, there'll be a moment here like where you have another change where you have the full torus. So in that sense, there is an analogy between like topology and physics in that sense that this would be your level set, so your potential surface. And then you could also have the same story about networks. So if you think networks as a universal way to encode information about a complex system, you basically associate vertices to nodes or areas, let's say in the brain or individuals in a society or name it. And then edges would be how they interact, hyper edges or simplicial complex, how they interact in high order. And then you would need to find some ways to find those slices. Oh, actually, if I would know this energy levels type of thing in a network, I could also mix this analogy with physics. So we do it in the brain networks. And then another relevant thing related to the question I had before is that there is this geometrical realization theorem in algebraic topology that a point cloud that you can represent as a simplicial complex is also, in a certain sense, a discrete high-dimensional space. So in a certain way, you can think of a simplicial complex as a configuration space. So then that's short. This slide was for the doctors. Is more like when you have also analogy with like a tomography. So there are many surfaces or 3D shapes, let's say like that has the same shape when you see it in pairwise, and therefore you miss stuff when you don't have a high dimensional representation of your data. And then one of the tools that is used to reconstruct high-dimensional structures on data is topology, like as we discussed, also hypergraphs and other things, but now it will be topology. And especially in neuroscience, because there is plenty of data available, not much theory available to model a brain perfectly. And then there's a big scholarship doing research on using topological methods in neuroscience. Of course, like Rickert is in the audience, so then what's high order for topology is not necessarily high order for other fields like information theory and statistics. So each field, the order high order, you mean different. But then I just want to mention that you have a lot of projects going on over the past years where you really could represent the data sets as simplicial complex. And for instance, that paper, you could really detect task switching. So you could create a based in TDA simplicial complex, in this case, like a specific representation, cluster representation of the brain that would change every time you do a task. And then all the type of examples. But then I want to show how does it work. So one nice thing, because I made this question, if you don't know the underlying model, you can still measure topological properties of the data. So not knowing the dynamics of the system, you can still measure the topology of the system. So then it's like, I don't know anything, but what can I do with the little that I know? And one example, that's the one I will actually focus now, is one of the simplest topological invariants. There are lots of topological invariants one can measure, but what I will focus now is the one that you know, like from high school, to the Euler characteristics, and you know why soon. Basically, we know for this polyhedra formula that for any polyhedra that is convex and without holes, you have this formula that vertex minus edge plus face equals to 2. This is a Platonic formula, and people thought that it was magic, but Euler made a demonstration why this formula holds. And actually, this has a lot to do with complex systems, phase transitions, especially also in the brain, and that's what I will show now. Not necessarily this version, but I will go to a more general version of this invariant. So in this specific case, the reason why, let's say theoretically, this is true is that all this polyhedra I've shown you is isomorphic to a sphere, and the sphere has all the characteristics true. So whatever the triangularization of a sphere you do, you have the same Euler characteristics. And then if you would have some genus, some holes, then this number will depend on how many holes you have in the surface. There's some funny jokes about between Euler and Beethoven, because like he was like a Swiss mathematician, but he was blind by the end of his career, and he still managed to publish lots of papers. Actually, after he died, people took like 20 years to publish what he left in manuscript, that he had his kids and some people helping him to make copies. He was dictating whatever maths he was doing, and because he was blind, and he still managed to make lots of mathematics papers. And the analogy with Beethoven is because Beethoven was also deaf, and he still composed. So it was interesting curiosity. Okay, but let's go back to the actual talk. So how can I relate this to phase transitions and brain networks and the previous chat I just mentioned? Okay, as I'll say, if I have a different number of holes, I will change this Euler characteristics. If I'm in high dimensional space, I can also compute Euler characteristics. And they basically, if you assume, okay, vertices are 0-dimensional structures, edges are 1-dimensional structure, faces are 2-dimensional structures, and then I can create high-order dimensional structures like simplexes. So basically, for every new high-order structure I can create in a topological sense, the Euler characteristic is basically the alternate sum of all high-order structures I have. So if I would have a tetrahedra, I would just put minus the number of tetrahedra, and then I would get Euler characteristics up to the tetrahedra. If I would have pentagons in a simplicial complex like this 5 to 5 connectivity, I would just add this term, and I would get also Euler characteristics. So it's a invariant that can be easily computable in any dimension, like no matter the simplicity complex I have, as long as I can enumerate all the simplex I have, the alternate sum of every simplex, and where the -1 to this sign comes to the parity of the simplex is the Euler characteristic. Okay, this easy is one of the cheapest invariants because one of the biggest problems in high order, okay, you have lots of advantages in high order networks, but one big problem is the scalability, because everything that's high order becomes very hard to compute. So one of the cheapest invariants is the Euler characteristic. And then how this relates to phase transition. So then I go back to these physics slides that I mentioned. So in physics, phase transition will be when you have a thermodynamic measurement, like something has a function of temperature, specific heat has function of temperature, magnetization has function of temperature. You have a non-analyticity in your thermodynamic function, and this non-analyticity is signature of a phase transition. That's so in the physics side. In a mathematics side, any function that you call thermodynamic function that can become for any field in mathematics, when this function is non-analytic, you may have a phase transition. So then that's make physics and maths to be in dialogue. So what happens, and that's the part that I will just storytell to you because I cannot show all the papers, is that if you have this, there is one analogy between microscopic world, phase space, and macroscopic world. So in physics, you would have all particles bouncing, and then you have energy, position, speeds, dynamics, and then you have phase space where you put all the particles and velocities in R to N, and then you get macroscopic properties. So you could also have similar stuff in topology. So you would also have all your simplexes, and then the whole set of simplexes is your simplicial complex, and this was some sort of phase space, and you have macroscopic measurements would be your topological invariants. So then you can have this analogy, so between whatever was made in statistical physics, like microscopic structures, that macroscopic measurements that's rooted on entropy. So when you got to this slide, like from microscopic world to macroscopic world, you connect them via entropy. It's known in theoretical physics that you can also make these connections via the Euler characteristics. So the higher the dimension you are in your space, you still can compute Euler characteristics, and this Euler characteristics grows extremely fast with the dimension of your space, and it's a measure of entropy, but it's a measure of topological entropy, not a normal entropy, but just topological entropy, because Euler characteristics can have negative values. So usually you start the logarithm of the absolute value of Euler characteristics. And what is known is that you could trace non-analysis in topology in the same way as in physics. So I showed 2 slides ago that a discontinuity in a thermodynamic graph is a signature of a phase transition. You could have the same for topology. So non-analysis in topological invariants, it's a signature of phase transition. And that was my first life, because after my PhD, I did some papers in this field. I didn't work straight in complexity. And then we had a few examples, some conjectures when this happens, when this is not happening. So that's like, there's a book. I should have also put this book as a reference, but it's a full book, so you don't need to see everything. But this book makes analogy between geometry, topology, and statistical physics in physics. And that's one of the strong analogies. Not for every physics model, this relation I'm telling you holds, but for a lot of models, this holds. Any questions? No? Okay, then I continue. And then there's a curiosity, because basically Boltzmann proposed this before we could observe the atom. So he suicided afterwards because no one believed in him. But then just 20 years later, there was Einstein making all these things and people measuring atoms and stuff. But then in his grave, there is a formula for entropy, because he basically proposed entropy, but just 20 years before was widely used, and also ergodic theory. All these things in probability theory came from Boltzmann. And what we show and other scholars show is that in some particular case, you could also use Euler as entropy. So that's what I just say. You compute Euler characteristics, or algorithm of this alternate sum of all simplex is a good candidate for entropy. And that's our analogy. Because I was one of those contributing it, if you Google Boltzmann graves, every nerd mathematician, this is like this Fields medal, I forgot his name, but the Fields medal from France with photos in Boltzmann's grave, and everyone goes to Vienna, they get photos in Boltzmann's grave. I also did that, so I put the Euler entropy next to his grave. I was a bit younger back then, but still. But the point is that how this connects with neuroscience and complexity and network science. So you could actually compute all these invariants. You just need to compute simplexes in data. So then if I have all the clicks, so there are several ways to assign a simplex to data. The easiest way is to compute the clicks of a network, like you get for your correlation matrix or for your pairwise adjacency graph, adjacency matrix, you compute all the clicks of a graph. So all the clicks of a graph, they can be considered simplex. It's the so-called click complex. And then when you compute this click complex, you
Yeah. Fernando, you were muted for some reasons. For the next.
Yeah, can you hear me again?
Yeah, but we lost like 30 seconds or something.
I'm sorry, that
Okay.
was my fault. Sorry for that.
Oh, okay. Where did I stop? Where was it when I stopped? Did you listen
We
when I speak
definitely
there?
heard this one. Yeah.
Okay, then it's this. So I was just telling that then in neuroscience or in complex systems, you can always, every time you can compute all the clicks of a network, you have a way to compute this topological invariant. So the phase in this formula, vertex minus edge plus face, the hyperface are basically the clicks of a network. So if you have adjacency matrix of a graph, all the clicks, like the all-to-all connection in this adjacent matrix, define a simplexes. It is called a click complex, and that would immediately give you the Euler characteristics of a graph. Of course, this is the easiest way to do that from empirical data. There will be other ways from data that you could estimate these clicks or these simplexes, like all different simplexes, but it's an invariant that you can always compute. And then, okay, that's happy face. So we can then make this analogy between physics and complexity. And then I make this table like that's directly analogy. That's what this slide, it has very different from the maths and from the physics one. So then it is most important for this part of the talk. So if you think in statistical physics language, you have your Hamiltonian function, microscopic word, go to macroscopic word. And if you think about topological language, you observe data as networks or simplicial complexes, and those are measured experimentally from data based on similarity measures, like correlation measures, high-order measures, like cumulant measures, whatever measure that you think can be a proxy for high-order interactions. Then you go, in the case of statistical physics, from microscopic word to macroscopic word, and then topology is from local to global, because you don't know which length scale your measurement is. So the local is just in a vertex level, global is the whole simplicial level. And then you have measure of energy, temperature, but in topology, thresholds for correlation, critical probabilities, etc. For in statistical physics, we would have Boltzmann entropy, but in topology with Euler entropy. So you have level sets, as I show in physics, and then you have a filtration process in topology, like you would keep adding nodes to your network. And then you have this phase structure that is like solid, liquid, and gases, etc. And what I will show is that the Bethe numbers will be the phases of your simple complex. And then usually in physics, you need to know, so that's why it's extrinsic, you need to know your equations to model the phase transitions. And in topology, you don't need, it's intrinsic. So it's just from the data. So then it's like friendly to big data. Okay, that's the analogy I would have. So the bigger analogy is like we have the speculation transitions, that this transition I just showed in the first part. And then you would have thermodynamic transitions, the physics version of this. So then that comes back to this brain paper. So basically you would start with an empty network and think as a Edus-Rényi type of network, zero probability. And then you keep increase the probability, you put more edge. So in that case, the brain is not random. So these connections are not coming at random, but every time I allow stronger or weaker connections to the brain, I have a transition that is also the Edus-Rényi type of transition. So if I keep adding more edge to the brain, so I put first the strongest edge, the second strongest edge, and so forth and so on until I end up out of edge. At some point, I'll have a transition, and this transition is also a generalization of Edus-Rényi transition. And because you saw the previous part, you see that this relates to the linear Pellet transition. And that's what we discovered. So if you get correlations, compute all the simplex, you can look for this invariant, the Euler characteristics, and these are like signatures of phase transitions. And what happened is basically this. So that's first, there's a way to compute this analytically. So there's not our result, but from Kinyu, this mathematician from Harvard. So there's a way for a random graph to get this expectation formula for Euler characteristics. But when you compute in an entropic form, so when you make entropy of Euler characteristics as function of probability in a random graph, you have all these singularities. And these singularities, that these spikes, are basically, according to the theory, phase transitions. And these transitions are then the Edus-Rényi transitions and all its generalizations. So basically, the first spike is what you see, what you already know, the Edus-Rényi transition. The second spike here will be Edus-Rényi transition for the first homology group. The second spike, the Edus-Rényi transition for the second homology group, and so forth and so on. So the emergence of every giant component in a random graph, like a generalized giant components or gigantic loops, like homological groups, homology groups, would come directly from the zeros of Euler characteristics. A nice way to see that is to put together the Euler characteristics plots with the Bethe number plots. So the Bethe number are the homology groups. So the connected components, they become only one connected component has a function of probability. And then there's like a single cluster, like the Edus-Rényi transition. And then all the other type of higher order components, they are localized in specific probabilities space. So then the first homology group is in only one specific probability range, the second homology group in another probability range, and so forth and so on. So each homology group is some sort of phase. That's the analogy between phase transitions and physics. And then if you do that to a brain, then you have a similar story. Like you do these in gray are like a few hundred brains, and in blue, this is like a average. And what we show is that these transitions exist in the brain, and it could be explained by this theory that I showed by Lineal and Pellet, and the previous theory on physics and topology and phase transition. And it's like old snap. Now the plots are getting beautiful, but this is an old paper. So how this would happen in the brain. So then you would increase the density, and you would see the emergence of these giant components, in this case, of triplets. And then, of course, the analogy again is like for very low thresholds, you have lots of trees. For high thresholds, you have giant components. And then you have this generalization for high order. So in each dimension, we would have this happening. And therefore, that's why you have so many zeros in the Euler characteristics and so many singularities in the logarithm for the Euler characteristics. And that's like what we found. Okay, then we applied that in different data sets. That's the data set from the human connectome, but we did also, I think someone asked about curvature. So we also notes that this could also have a local counterpart, because probably some of you heard about this Gauss-Bonnet theorem. So integral over a surface is proportional to the Euler characteristics. So the sum of curvatures in a surface is proportional to Euler characteristics. So then we use this theorem, like how we can get Gauss-Bonnet theorem for simplicial complex, and then we can define curvatures for networks. And there was also a paper that points out that curvature goes to 0 near phase transition, and also that's what we found. So that's also related to other papers that studied the distribution of cliques and simplex in the brain. That's the one that the main reference from Sizemore. And that's what I just mentioned. Like if you have like I don't have the plots of the simplex here anymore. I just define this curvature in the brain, and then every node you have a local number that's the curvature, and then this is the distribution of curvature before phase transition. During a phase transition, you have 0 curvature, and after positive curvature. I think I made that video that you can see this transition happen in terms of curvature. So I'm just computing curvatures in the brain, and then around the transition, you have like nearly every node 0. So the size of the node is the value of curvature. And then you have a switch from like negative curvature to positive curvature. And every time you have a transition, you switch to another signal curvature. And that gives like a local metric, which is like cheaper to compute because you don't need, it's all local. So to finish that, then I go to the questions. I basically, we applied this to glioma data set, and that was with Linda. That's also part of our network. So you use a glioma data set and a control data set, and you show that there is a difference, statistical difference between the glioma and control data sets if you want to extrapolate the physics insights. Because let's say in physics, we know that let's say everything that boils at 100 degrees at sea level is very likely to be water. So the phase transition point is a property of that material. Of course, it's not one-to-one, so you could have 2 different materials with the same boiling point, but you can have a property that's necessary to be from the same materials at the same phase transition point. So then with this in mind, you could just check whether these topological transitions, they classify or they are different from other one system to another. And then we've shown that between glioma and control, this is true. And that was very nice because we basically, in our paper, we made the whole bridge from theoretical papers that I just showed in the beginning and how you can apply and the analogy physics. And then we show in the brain that this is the case. And after that project, there are many other applications with the same logic. Like you study the Euler number and then use it as an entropy. And then the transition that you can see via Euler number are this type of generalized percolation transitions. Another author called it homological transition because it's related to homology. But that's what we kind of found. So basically, that's like what we did. This slide I had no, I didn't have a question. Where is it? Where's my, sorry, how can I stop? Sure, yeah. In this slide, I had a question in the other slide, but the question is very simple. And one of you already made this question, true. I'm spoiling because Cyril did a master's at UVA under my supervision, and I'm very happy about it. But the question I would put now is that, okay, I've shown one example where you have some methodology that comes from mathematics into physics that we translated to networks and high order structures. So in the sense, a phase transition really came from either maths if you go to Eros-Reini, or physics if you go to thermodynamics. And then you can get network structures and also check for phase transitions with similar methods. And in that specific case, we really came, okay, this generalized entropy induced phase transitions, and we get a result that's comparable to this type of analogy. Then here comes the question for the breakout room. So is it possible to have other analogies in that way for other metrics in physics or in mathematics that you would just come in high order and measure? I did this for the phase transition, but I know that Ginestra Bianconi, she already talked to BeyondTheEdge a seminar series. She made quite a few work that are like that. Like she found a Bose-Einstein condensation. This is like a condensation that exists in physics. She found in a network. She has several models that does this type of analogy. So then I have the question, like, do you think it's possible to make these analogies? And if so, which ones would you be your favorite ones? And Sirio is the first one to answer because I know you can answer this. Okay, that's now breakout rooms.